In the last two lectures, we introduced some of the most basic circuit elements that we will be using in this course: voltage and current sources and resistors. In this new note packet, Kirchhoffs Laws and Equivalent Circuits, we're going to be introducing the fundamental circuit analysis theorems that are used in conjunction with the VI characteristics of the different circuit components to solve circuits. So in the book, you want to read sections 2.3 to 2.5, 3.1 to 3.5, and 4.9. So what we're going to do in this note packet, we are first going to briefly talk about what we mean by series and parallel connections, because you need to understand this before we get into the Kirchhoffs laws. Then we will establish the two most fundamental laws in circuit analysis, Kirchhoffs voltage and Kirchhoffs current laws. And then we'll start talking about different types of circuit analysis. So the first thing we need to do is define what we mean by a series connection and a parallel connection. Suppose you have a node that is connected to exactly two elements, let's say A and B. We then say that elements A and B are in series. And a fundamental result is that all the current that flows through A also has to flow through B. An important point is that these two components, A and B, have to be the only two elements connected to this node between them. If you have a third element here, these are no longer considered to be in series. When you have two components that are in series, they have the same physical current. If you have current variables, they're going to either be identical or opposite in sign. In this example below, for example, R1 and R2 are in series because they share the same node up here. We have two different current variables, IR1 and IR2. IR1 is the current flowing through R1, IR2 is the current flowing through R2. Because the current arrow direction is opposite for IR1 and IR2, we see that they are not the same, they are opposite of each other. So bottom line, R1 and R2 have the same physical current, but the variables are going to be opposite. One might be 5 milliamps, the other one would be negative 5 milliamps, specifically because the way we're defining the currents is different. So they have to have the same physical current, but the defined currents are the same two within a sign. Another important point in series connections, if A and B are in series because they share this node, and B and C are in series because they share this node, then we say that A and C are also in series. Once again, if you think about the physical current that flows through it, whatever current is flowing through component A has to flow through component B, has to flow through component C. Another important point with series connections is the fact that two elements that might be in series might not be in series if you start adding things to the circuit. So imagine a circuit now with maybe some stuff out here, and then you have component A here, a component B there. So they are connected by a single node right there. And if we have nothing connected across these terminals here, we call that a port, then A and B will be in series. Whatever current is flowing through A has to flow through B. So A and B are in series in this situation. However, if we connect something up to these two terminals here, let's say we connect up another component here, C, A and B are now no longer in series because the current that flows through A, some of it's going to go through B, but some of it is also going to go through C. So the bottom line is just because two elements are in series doesn't mean they're always going to stay in series once you start adding things to a circuit or connecting things up to a circuit. Let us define parallel connections now. Suppose you have a node on top here, and remember, anything that's connected by just a wire is considered one node. So that is one node on top, and this is one node on the bottom. If you have two or more circuit elements that are connected to the same two nodes, we say that those two elements are in parallel. So components A and B are in parallel. So when elements were in series, they shared the same physical current. when elements are in parallel, they share the same physical voltage. So whatever voltage is across element A is also going to be across element B. So they have the same physical voltage. What we mean by that is if there is 5 volts across one, 5 volts across the other. But just like with currents, you do need to take a sign into consideration when you're looking at variables. For example, in this example down below here, component R1 has a voltage across it VR1, where the plus terminal is defined as the plus 1. R2 is in parallel with R1, and we define a variable VR2 across R2, but we arbitrarily put the plus down on the bottom. So although R1 and R2 share the same physical voltage, their voltage variables, VR1 and VR2, are opposite. Specifically, VR2 is equal to minus VR1. So elements in parallel share the same physical voltage. Their voltage variables are either going to be the same or maybe opposite in sign, depending upon how you arbitrarily define the plus and the minus. Once again, we have to remember, the fact that there is a plus here does not necessarily mean that this node is at a higher voltage than this node. VR1 is just a variable. In fact, if you look at this example here, one of these has to be a negative number. Either VR1 is going to be negative or VR2 is going to be negative because of how we defined those variables. Now that we have defined series and parallel connections, we are ready to develop Kirchhoffs laws. First thing I want to point out is the spelling. There are 2 H's in the middle of Kirchhoff, so make sure you get that right. So Kirchhoffs laws were named after Gustav Kirchhoff, who was a German physicist who lived from 1824 to 1887. Kirchhoffs laws themselves were established in 1845. So what are Kirchhoffs laws? They are constraints on the currents and voltages in a circuit due to the interconnections between the different circuit elements. And we're going to see the Kirchhoffs laws in conjunction with the IV relationships for the specific circuit elements, the sources, the resistors, the capacitors, etc. The Kirchhoffs laws in conjunction with these IV relationships are going to form the basis for circuit analysis. Specifically, we're going to see that if we simultaneously use Kirchhoffs laws and the IV relationships of the circuit elements, we can come up with a set of equations to solve circuits. And we're going to see that there are 3 basic ways to solve circuits. The first approach is the ad hoc approach. In the ad hoc approach, you just start randomly writing equations down and you hope that you come up with enough equations to get the correct answer. When you first learn circuit analysis, this is probably how you try to do it. This is not the best approach for solving circuits because you often end up going around in circles and you sometimes write more circuit equations than needed. A second approach to solving circuits is a simplification approach. In the simplification approach, the idea is to use different properties and rules and theorems to simplify the circuit to make it easier to solve. We'll be spending quite a bit of time using this approach to solving circuits. The third approach is an algorithmic approach where you very systematically write the different equations that you need to solve the circuit without simplifying the circuit first. We will also be spending a lot of time solving circuits this way. The simplification approach is covered in Chapter 3 of the book and covered in Chapter 4 in sections 4.9 to 4.13. We will look at the simplification approach first. The algorithmic approach is covered in the book in chapters 4.2 through 4.8. We will look at that method second. So the first of Kirchhoff's 2 circuit laws is Kirchhoff's voltage law, which we will abbreviate KVL. Kirchhoff's voltage law specifically says that the algebraic sum of the voltage drops around a loop is 0. In other words, what we're saying is if you start at any point in a circuit and travel through any loop in the circuit back to that starting point, and you sum up the voltage drops as you go through the different elements, by the time you're back to the starting point, your net sum is 0. A good analogy would be if you're on a hike and you're at a certain elevation. Remember, elevation or altitude is like voltage. If you're on a hike and you're at a certain elevation and you go on the hike, regardless of where you go on that hike, you're going to get elevation gains and losses as you go up hills and down hills. When you end up at the starting point, your net elevation gain is 0. So the algebraic sum of voltage drops around a loop is 0. When you first learned Kirchhoffs voltage law, you might have learned a different alternate, which basically says the algebraic sum of voltage rises around a loop is 0. This is really saying the same thing, except what you're considering a plus would be a rise versus a plus being a drop. Once again, the analogy with a hike. You can either measure your elevation gains or you can measure your elevation losses. It really doesn't matter which way you do it, the net is going to be the same. Another alternate is you basically put on one side of the equation all your elevation drops, and on your other side of the equation you put all the elevation gains, and they have to be equal to each other. These are 3 ways of saying the same thing. However, for reasons that I will explain in a minute, I think it is best to sum voltage drops around a loop. So let's look at a quick example down here. Suppose you have a circuit here with 4 different elements, A, B, C, and D. We really don't care what they are. You can define many different loops. For example, one loop you can define is this square loop here. So you can start at any point on the loop. You can go either clockwise or counterclockwise, and we're going to sum voltage drops. So we will start at this point here, and I'm going to go clockwise. So as we go through element A, we get a drop of VA volts. Then we continue on the loop, we go through element C, and we get a rise of VC volts or a drop of negative VC. Then we continue on in the loop and we go through VB, and once again it goes from a higher to lower voltage, so we get a drop of VB. So we get VA minus VC plus VB is equal to 0. The reason that I like to do voltage drops is, notice if you hit the plus sign first, you write plus. If you hit the minus sign first, you write minus. When you sum up voltage drops, you do that. If I were to use this alternate 1 and do the algebraic sum of voltage rises, and I start at the same point on top here and go clockwise, I would write it as negative VA plus VC minus VB is equal to 0. Notice it's the same final equation, but I find it's easier to sum voltage drops because you can get the sign directly just from looking at whether you hit the plus sign or the minus sign first. So that's loop 1. Loop 2, let's make it this big loop here. Let us start this one arbitrarily at this blue node on top here. And in this case, I'm going to go counterclockwise. Once again, Kirchhoffs law doesn't care whether you go clockwise or counterclockwise. It doesn't care where you start. All that it cares about is that you end up where you start. So starting at this blue point and going counterclockwise, we first go through component A, and we hit the minus sign first, so it's minus VA. Then we go through VB, we hit the minus sign first, so it's minus VB. Then we go through component D, and it's another rise of VD volts, so the drop is minus VD. So we get minus VA minus VB minus VD is equal to 0 because I am summing voltage drops. If I was summing voltage rises, I get VA plus VB plus VD is equal to 0. It's the same equation. If I went clockwise, guess what? I would get the same equation, maybe written in a different form. But regardless of whether I go clockwise or counterclockwise, regardless of whether I start at this node on the top right or the node on the bottom left, regardless of whether I do voltage rises or voltage drops, the equation might look different, but once you manipulate it, you'll see that they all give you the exact same equation. So there are multiple ways you can construct the equation. When it's all said and done, it is the same equation. So the third loop we're going to do now, we'll use a different color, we'll use this yellow, is going to be sort of this L-shaped loop like this. Once again, I can start whatever point I want to start at, and I can go either clockwise or counterclockwise. I'm going to start the same node I started at last time. I'm going to go clockwise. So I go through component D, I hit the plus first, I get a voltage drop of VD volts. Then I come around here, the only other component I hit is VC. Once again, I get a drop of VC volts before I get up to the starting point. You get VD plus VC is equal to 0. As with the other two loops, it's totally arbitrary that I went clockwise. It was totally arbitrary that I started in the top right node, and it was somewhat arbitrary that I did voltage drops rather than voltage rises. You can get the same equation using different approaches. Once again, though, I find that it is easiest. In my opinion, the easiest approach is to first off always choose the same direction. I like to always go clockwise, although in one of these examples I did go counterclockwise. Second approach is always sum the voltage drops. The reason you want to do that is if you hit the positive terminal first, you write plus in the equation. If you hit the negative terminal first, you put a minus in the equation. An important caveat regarding Kirchhoffs voltage law is that you cannot have a set of voltage sources being the only elements in any loop. What happens if you have any loop where you only have voltage sources, you cannot simultaneously have independent choice of what those voltage sources can be and also guarantee that KVL is met. So for example, if you look at this circuit on the right here, here is a loop where the only components are voltage sources. The problem with that, suppose these voltage sources were values of 10 volt, 5 volts, and 10 volts. If you did KVL, you would get negative 10 plus 5 plus 10 is equal to 0, which is not true. So you're violating KVL. This also means that you cannot have two voltage sources in parallel that are different values for the same argument. So on the left here, if you try to do a KVL here, you would get minus V1 plus V2 is equal to 0. And let's say, for example, that V1 was 5 volts and V2 was 10 volts. You would get minus 5 plus 10 is equal to 0, which cannot happen. So the bottom line is, in a circuit, you will need to avoid the situation where you have any loop consisting only of voltage sources. Now, as long as there's at least one other component in there, for example, a resistor there or a resistor here, then you no longer have this problem because the resistor's voltage is determined a different way, and that could be adjusted so that you get the voltage drops adding up to 0. So you cannot have a parallel connection of ideal voltage sources, and you cannot have a loop where the only components are voltage sources. So this gives rise to two questions. First question is, what happens if you do this then? Will you go to jail? Will you blow up the world? In practice, voltage sources all have a very, very small series resistance with them. So what that means is technically you are not connecting just voltage sources in a loop because of these series resistances that are associated with the voltage sources. What happens, however, in a situation such as on the right, you would get very, very large currents if you try to connect up voltage sources that didn't add up to 0. So there would be very small resistances in the circuit that would keep you from technically violating KVL, but it would give you a situation that you really want to avoid with very, very large current flows. The second question is, you might ask, well, wait a minute, what about batteries in parallel? You have devices where you stick two AA batteries, and those batteries are going to be in parallel. And your first question might be, isn't that a violation of KVL? Well, let's look at that on the next page. So first off, as I mentioned before, whenever you have a real voltage source, is a very small resistance in series with the ideal voltage source. So if you connect two batteries in parallel, such as this example here, technically the voltage sources themselves are not in parallel because of the two resistances. So this ideal voltage source and this ideal voltage source are not in parallel because of these two resistors. The other thing that's an important point here is that these voltages are the same. You do not connect a 1.5 volt battery in parallel with a 9 volt battery. You connect it in parallel with another 1.5 volt battery. So because these are the same values, connecting them in parallel is allowed. So then the question is, why would you want to do this? If this battery gives you 1.5 volts and this battery gives you 1.5 volts, isn't this redundant? The reason that you sometimes would connect batteries in parallel is that they share the burden of providing current to the load. And we will see this later on this semester. So this voltage source, this battery would provide some current, and this battery would provide some current, and both of those currents now would drive this light bulb here. But as I said on the previous page, if you have a situation where these two voltages are not identical, you would get very, very large currents flowing in the circuit. And what that would do is that would drain the batteries and also create some dangerous heat. Bottom line, as we said on the previous page, you never connect voltage sources in a loop where you violate KVL. The only time that you would want to connect voltage sources in parallel is if they are the same value, such as in a situation with the battery here. Let's talk about Kirchhoffs current law now. So KCL is Kirchhoffs current law. Kirchhoffs current law basically says that the algebraic sum of the currents leaving a node is 0. So good analogy here, if you have a whole bunch of pipes connected together, and there's a connected with a joint here, the sum of the flow out of that joint is going to be 0. In other words, water is not going to accumulate at that joint. You might have some water flow in and some water flow out, but the net sum at this point in the middle is going to be 0. Kirchhoff's current law is saying the same thing, except we're talking about movement of charge, electron current, as opposed to water current. Just like Kirchhoff's voltage law, there are a couple alternative ways to say Kirchhoff's current law. The definition I like to use is the one that says the algebraic sum of currents out of a node is 0. But you could equivalently say that the algebraic sum of currents into a node is 0. So whether you sum them going out of the node or into the node, it doesn't matter. It's going to give you the same ultimate equation. A third alternate says that the sum of the currents out of the node is equal to the sum of the currents into the node. For example, here, green equals the 2 blue. Okay, let's do an example with the circuit here. So here we have a circuit. We don't know what the components are, but we have 4 different components, A, B, C, and D. If you think about the nodes, remember what a node is. A node is any point or groups of places connected just by a wire. So there's one node on top here, and I have the same circuit drawn on the right with right angles. You have a second node down here, which is this node, and a third node right there, which is that node. So let's look at node 1. If we sum the currents leaving the node, the current in this direction is IA. The current in this direction is IB. The current in this direction, IC is the current through that loop, but notice that IC is defined as a current going in this direction. So the current in this direction is negative IC. So we get IA plus IB minus IC is equal to 0. A good way to remember whether to write a plus or a minus, if you hit the tail of the arrow first, you write plus. If you hit the head of the arrow first, you write minus. So we get plus IA plus IB minus IC. Now, if we did the algebraic sum of the currents into the node, you would write the KCL equation for node 1 as negative IA minus IB plus IC is equal to 0. Notice it's the same equation when it's all said and done. If you used alternate 2, you would write it as IC equals IA plus IB. So whether you do it the way that I recommend or the other two ways, it really doesn't matter. It's personal choice. They all give you the same equation. So it's either IA plus IB minus IC is equal to 0, or negative IA minus IB plus IC is equal to 0, or IA plus IB equals IC. Okay, let's do the same thing for node 2. Once again, I like to sum the currents leaving the node. So this current plus this current plus this current is equal to 0. The current in the left direction, it's IA, but you hit that arrow head first, so it's minus IA. Likewise, the current in this direction is IB, but it's minus IB because of the way IB is defined. So it's minus IA minus IB. And once again, this current is ID, but you hit the arrow head first, so it's negative IA minus IB minus ID is equal to 0. Using alternate 1, it would be IA plus IB plus ID is equal to 0, etc. Node number 3, that is this node on the bottom right. Current in this direction plus the current in this direction have to equal 0. Current going up is IC. We hit the tail of the arrow first, so it's plus IC. Going to the left, we hit ID. We hit the tail of the arrow first, so it's plus ID. So we get IC plus ID is equal to 0. Once again, if we did a sum of the currents entering the node, we would get negative IC minus ID is equal to 0. It's the same equation. My recommendation is to sum the currents out of a node. I find that to be the easiest, but you are really welcome to use any of these 3 approaches that you are comfortable with. The important thing is that you are consistent. You don't want to do some nodes where you're summing currents entering and other nodes where you're summing the currents leaving. You are bound to make mistakes if you are not consistent. Kirchhoffs current law says that the sum of all currents leaving a node has to be 0, but it's actually more general than that. Kirchhoffs current law says that if you can draw any circle anywhere in the circuit, which, by the way, that circle is called a Gaussian curve, also called a supernode, we'll see later on. But if you can draw this circle anywhere in the circuit, the algebraic sum of the currents flowing out of that circle is going to be 0. So, for example, in the bottom left here, we have multiple circuit elements. And we know that for a particular node, the sum of the currents leaving that node is 0. But we can be more general. We can now draw a circle anywhere in the circuit. For example, right here. Kirchhoffs current law says that the sum of the currents leaving that circle is 0. So it leaves at this point, so that's that current. Leaves at this point, that is that current. Leaves at this point, that is that current. So we get that IA plus IB plus IC is equal to 0. And even if you had more components in here, for example, maybe there's a component here that looks like that, we still have that IA plus IB plus IC is equal to 0. So you can define a whole bunch of Gaussian curves anywhere in the circuit, and we will see there are times where we want to do this in circuit analysis, and Kirchhoff's current law still holds. It goes the other direction as well. So if you look at this circuit on the right, this thing in yellow is one node. And let's define a couple more currents, by the way. Let's call the current through this component ID, and let's call the current through this component IC. So this thing in yellow is one node. So if you did KCL for that node, you would get this current plus that current plus that current plus that current is equal to 0. So you would get IC minus ID. Why is it minus? Because we hit that arrowhead first, plus IA minus IB minus because we hit that first is equal to 0. So that current plus that current plus that current plus that current is equal to 0. So this would be the KCL equation for that node. But we could, if we wanted to, draw this Gaussian curve right there. That is a portion of a node. So technically, this point here is the same node as this point here. It's one node. But we can break it up like that and then find the current leaving this subnode, if you want, by defining this new variable Ix, which is the current through this wire connecting these two parts in the circuit. If you do that and write the KCL equation, you basically get what? You get this current plus this current plus that current is equal to 0. So the current going down is IA. The current going up is negative IB, and the current going to the left is IX. So we get two different equations here. If you do this subnode, so to speak, you get Ix plus IA minus IB is equal to 0. If you consider the entire node, you get IC minus ID plus IA minus IB is equal to 0. Both of these are valid. So we will see that there are times in circuit analysis where we want to create these Gaussian curves, or the supernodes as we call them, and do Kirchhoffs current law for them rather than Kirchhoffs current law for a specific node. It's valid either way. If you remember, in Kirchhoffs voltage law, we said you cannot have any loop that is consisting just of voltage sources, and related to that, we say you cannot have two voltage sources in parallel, unless of course they are the same value. We talked about that as an exception. Likewise, in Kirchhoff's current law, you cannot have any Gaussian curve where the only components connected to the outside of that are all current sources. So if you look at the situation on the right, we have a Gaussian curve, and we have connected to that current source, current source, current source. This is not allowed. The reason being, suppose IA is 10 milliamps, suppose IB is 5 milliamps, suppose IC is, let's make it another 5 milliamps. From KCL, we know that this current plus this current plus this current would have to be 0, so we get 10 plus 5 plus 5 is equal to 0, which is obviously not true. So you get a violation of Kirchhoff's current law. A subset of this is you cannot have two current sources in series, because if you had these in series, you have a node there. This current would have to equal that current. You would have that I1 minus I2 would have to be 0, but what if I1 was 10 milliamps and I2 was 5 milliamps? you would then get 10 milliamps minus 5 milliamps is equal to 0, which once again is not allowed. Common mistake when students look at something like this, you might be inclined to think, okay, if you have a 10 milliamp and a 5 milliamp current source in series, why does that not just give you 15 milliamps? Because 10 plus 5 is 15. It doesn't work that way. If the 10 and the 5 milliamp sources are in parallel, yes, they would add up to 15. But in series, it is a violation of KCL. If you think about it, what this is telling us is that this branch of the circuit is going to have 10 milliamps regardless of anything else. What this source is telling us is that this branch is going to have 5 milliamps regardless of anything else. But because they are connected in series, the same current, the same physical current has to flow through both, and 5 cannot equal 10. So, you got to remember, you do not put voltage sources in parallel if they're different, and you do not put current sources in series if they are different. Let us finish off this lecture with one simple example illustrating how KVL and KCL can be used to solve some simple circuits. So here we have a circuit with a couple voltage sources, a couple current sources, a couple resistors, and we have two unknowns. We have Vx, which is the voltage across that 4 ohm resistor, and we have Iy, which is a current through this 2 ohm resistor. So the idea behind using KVL and KCL is to see if you can find some equation where the only unknowns are the Vx and the Iy. So your first inclination might be, okay, let's try to do KVL and let's try to sum the voltages, voltage drops across these elements. So you know the voltage drop across a 12 volt voltage source is 12 volts. Vx, the voltage drop across a 4 ohm resistor, is what we're looking for. But we don't know what the voltage drop across the 2 ohm resistor, and we certainly don't know the voltage drop across the 4 amp current source. So this loop really doesn't give us a solution. However, if we choose this loop, the only unknown voltage is Vx. So if we do KVL along this yellow loop, we'll start at that green point, and I'm going to sum voltage drops. So doing KVL, starting here, I'm going to go clockwise. I get minus 12 volts. I hit the minus sign first, so I write it as minus, plus Vx, that's what I'm looking for. Continuing on, minus 2 volts. Continuing on, plus 6 volts. I'm back to where I started. Set that all equal to 0. The only unknown is Vx. You can solve for that. You get Vx has to be 8 volts. So this works because we know the voltage drop across that. We know the voltage drop across that. We know the voltage drop across that. This is our only unknown. So let's say we want to find the current Iy. So to find currents, you typically want to use Kirchhoffs Current Law. So let's find a node, and here's a logical node here. And what we know is that all the currents leaving that node have to be 0. So that current plus that current plus that current has to be 0. So using KCL, the current to the left, it's at 4 amp source, and notice this arrow is going in the same direction as this arrow, so it's 4 amps. Current going up, current through that 2 ohm resistor is Iy, but because I hit the current arrow first, it's minus Iy, because I'm summing the currents out of the node. And then current to the right, once again, it's a 6 amp, but I hit the current arrow first, so it's minus 6 amps is equal to 0. So we get 4 amps minus Iy minus 6 amps is equal to 0. Solving for Iy, you get Iy is equal to minus 2 amps. Once again, if I sum the currents entering the node, I would get a similar equation. I would get -4 plus IY plus 6 is equal to 0. Guess what? You would still get the same answer of IY equals -2 amps. One thing I should point out here, if I try to do KCL at this green node up here, certainly that current plus that current plus that current does equal 0. However, when I try to write the equation, what's the current in this branch to the left? We don't necessarily know that. And what is the current in this branch to the right through this 2-volt source? We do not know that either. So although certainly the sum of these three currents does have to equal 0, it doesn't give us this answer easily like it does when we use this node. Next class, we will continue by looking at a slightly more complicated example and see that if you don't have an organized way of writing these KVL and KCL equations, you can easily get overwhelmed very quickly. And then we'll start coming up with more precise ways to solve circuits. Have a good day.